topic is linear programming, so you want to present the form of a typical linear program. Then we're going to go through an example involving crude oil purchasing that involves two decision variables. And the nice thing about two decision variables is then you can get a plot by constructing a feasibility diagram, and therefore the analytical solution is very clear. So the general form of a linear programming problem is you have a linear objective function. So here we're showing that X is the set of decision variables. Those are the variables that are adjusted to solve the optimization problem. And so we're trying to minimize this objective function by adjusting the decision variables X. And you can see that it's linear in X because it's just the sum of coefficients C1 times X1 plus C2 times X2, et cetera, up to Cn times Xn. We also have bounds on the decision variables, some lower bound and some upper bound for each one of the decision variables. We have inequality constraints that are a function of the decision variables. And we also have possibly equality constraints, often through the form of modeling equations that are functions of the decision variables. So the way this is generally written in the optimization literature is shown on the right-hand side using matrix vector notation. So then you have this row vector C transpose times the column vector X, and that represents the linear objective function that's being solved, subject to the bounds on the decision variable vector. The inequality constraints represented as AX is less than or equal to B, and then the equality constraints. So we're going to take a simple crude oil purchase processing decision problem. I should note that these prices are about 1/2 the current prices for crude oil and for the various products. We have crude oil 1 at $24 per barrel, crude oil 2 at $15 per barrel, and then possible products that can be produced: gasoline, kerosene, fuel oil, and resid, all with different values. Gasoline, the highest value, and this heavy resid, the lowest value. Now we need to have some relationship. We need to know what the yield of each of these products is from each crude. So for example, crude oil 1 will represent a lighter crude. And from crude oil 1, you get a yield. So of every barrel of crude 1, you get 80% gasoline, 5% kerosene, 10% fuel oil, and 5% residual. And the cost to operate crude oil 1 is 50 cents per barrel. Similarly, for crude oil 2, it's a heavier crude, so it produces less gasoline. So the yield of gasoline from crude oil 2 is 44%, kerosene 10%, fuel oil 36%, and resid 10%. And notice that it takes more, it's a higher operating cost to process crude oil number 2. It's $1 per barrel rather than the 50 cents per barrel for crude oil 1. Now, each of these products has a maximum amount that needs to be produced. So, for example, this could be constraints either due to product demand or maybe even product storage. So we can produce a maximum of 24,000 barrels of gasoline, 2,000 barrels of kerosene, and 6,000 barrels of crude oil. There's no particular constraint on the resid. So now we're going to go through and see how we write these relationships. So it's really the material balances are what results in the constraints. So for gasoline, because the yield from crude oil 1 for gasoline was 80%, that means whatever value we have for the crude oil in terms of number of barrels that are going to be processed, then 0.8 times that value, X1, plus 0.44 times X2, because the yield of gasoline from crude oil 2 is 44%. So that's the amount of gasoline that's being produced, and the constraint is 24,000 barrels of gasoline. Similarly, with kerosene, 5% of crude 1 plus 10% of crude 2 has to be less than 2,000 barrels. Then finally, the fuel oil, 10% of crude 1 plus 36% of crude 2 must be less than 6,000 barrels. Now, there's no particular constraint on the resid, so that doesn't appear. It will have an effect because that's going to appear in the net income. Now, what you want to do is construct a feasible region by plotting the material balance constraints on an X1, X2 plot. Again, that's a nice thing about having two decision variables. So we're going to want to plot each of these three material balance constraints on an X1, X2 plot. And so that's what I've shown here on the lower right-hand side. I have the X1 axis, the crude oil 1 in terms of thousands of barrels per day. The y-axis or X2 axis for crude oil 2, again in thousands of barrels per day. We want to represent each of these material balances with constraints as a line on this plot. So you can either look at this as the endpoints of the line, which in the case of gasoline would be 0 for X1, 54.5 for X2, and then 30 for X1, 0 for X2, draw the line between those 2 points. Or similarly, if we solve for X2 as a function of X1, then you can write this relationship and basically go from an X1 value of 0 across the graph. So do this right now on your own. So pause the screencast and draw these material balance lines which form the constraints in our problem. Okay, so we've constructed the material balance constraints. So for gasoline, we find this blue curve. And so we have to be inside this region that's less than the blue curve. Similarly, the red represents kerosene, and we have to be underneath that red region. And finally, the fuel oil shown in green is we have to be underneath that region. So the next plot, I'm going to blow this up and show it on a different scale because we have to be underneath all of these curves, and that's what forms the feasible region for our solution, so that all the different constraints are satisfied. So again, I blew up the plot from the previous screen, and the yellow is the feasibility region. So again, we had our kerosene constraint in red, we had the gasoline constraint in blue. So we can see that we form one intersection in green with the fuel oil and the kerosene. So that's one kind of node or intersecting point here. There's another with the gasoline and the kerosene. And so again, we have to satisfy all those constraints simultaneously. So our solution must be in the yellow region. We haven't discussed anything about economics yet. So now we want to add economic lines related to the net revenue. So here we have the product income because the values of each of these products, gasoline, kerosene, fuel oil, and resid, and the yields from each crude oil 1 and crude oil 2. So we need to sum up the product income and then subtract off the costs of processing and the purchasing or the value of the crude oil. And so when you do that, what you find is you have a net revenue relationship that's shown in green here that's ultimately, once you work through the algebra, $8.1 per barrel times the number of barrels for crude 1 plus $10.8 per barrel times the number of barrels for crude 2. Now, for simplicity, what we can do is then solve for X2 as a function of X1 for different values of that revenue. then we can plot lines of constant revenue on the feasible region plot. And so that's what I've done here. So this bottom line represents a net revenue of $200,000. And this dash line at the top represents a net revenue of $300,000. But notice it does not satisfy any of those constraints, whereas the 2,000 line satisfies constraints, but it's clearly not maximizing the net revenue. So we need a constant line that's parallel to the $2,000 and $3,000 that still satisfies the feasible region, but we want the maximum value for that operating line. And when you go through this, what you find as you move between the $200,000 and $300,000 is an operating line of $286,000 is what just satisfies this constraint. And that turns out to be the intersection of the gasoline and the kerosene material balance constraint curves. And what you find is this solution is at 26,000 barrels of crude oil 1 and 6.9 thousand barrels of crude oil 2. So now we know the solution, we know how much crude oil we need to process, and then we can find the total amounts of products that are actually being produced when we go back to our material balance equations, because again, from that yield table, gasoline was 80% of the yield of crude 1 and 44% of the yield of crude 2. And so then when you go through that calculation, you find this set of products of gasoline being 23.8 thousand barrels, kerosene 2, fuel oil 5.1, and resid 2, and they sum up to the total of sum of crude oil 1 and crude oil 2. Now, this can also be formulated mathematically in the following fashion. And so in the next screencast, we're going to go through and show how to use MATLAB to solve this problem using this mathematical formulation. But again, the revenue curves we showed were 8.1 times the amount of crude oil 1 plus 10.8 times the amount of crude oil 2. Now we wanted to maximize the revenue. So for using a minimization statement, the minimum then has to be the minus of the function that we want to maximize. Then we had bounds on crude oil 1 and crude oil 2, and only bounds are on lower bounds. So we had infinity for the upper bounds. We did have constraints. Remember, we could only produce 24,000 barrels of gasoline, 2,000 barrels of kerosene, and 6,000 barrels of crude oil. And so then that appears in that inequality constraint. The way we formulated the problem, we did not have any equality constraints. To summarize, we discussed the form of a linear program. We solved a problem involving two decision variables by constructing a feasibility diagram. And then we used a crude oil purchasing example.